Okay, so this next lecture is a little bit of a mixed bag. I'm going to tell you a little bit about mixed integer rounding cuts. And then I also have a little example of a nonlinear reformulation that's maybe not as standard, where you can use some tricks to get a formulation that's computationally easier to solve for nonlinear optimizers. So I'll get to that at the end. But we're still thinking about generating cuts for our branch and cut algorithm. And so the goal is to strengthen mixed integer linear optimization relaxations so that we can solve them. The feasible set becomes smaller for example, in our branch and cut algorithm. And so what we want to do is iteratively add cuts to remove fractional linear optimization solutions. And so one very easy set is the set that's given here, where we have just two variables, a continuous variable x2 and a continuous variable x1 and integer variable x2. And it is just given in terms of this very simple constraint here. And x1 is non-negative. And then you can show that you can strengthen this inequality by rewriting it in this way down here. So this cut is actually a valid cut for this set. So I have a little example to show this. So the mixed integer rounding cut that we would get for this constraint here is given on the right-hand side there. So let's write this constraint down. It's x2 less than or equal to 2x1. And then we'll just go back to the recipe. And the recipe said that I need to rewrite it as x2 less than or equal to, I think I have the wrong one. It's derived from that, okay, sorry. The original cut, the original constraint, that's the one we want to write down. The original constraint is x2 less than or equal to a half plus x1. And then the formula for deriving it is x2 less than or equal to the floor of the constant on the right-hand side. So that's the floor of a half plus x1 divided by 1 minus the fractional part of the right-hand side. So b minus the floor of b is the fractional part. So that's 1 minus, and that's a half minus 0. And so that's just simply 0 plus x1 over a half or 2x1. And that's the cut that we'll get. And so this cut is then illustrated. This weaker cut was here. That was the weaker cut. And so the stronger cut is then the one that cuts through these two feasible sets and gives you, again, the convex hull of the two feasible sets that you have here. So x1 is a continuous variable, x2 is on the horizontal axis, and you can cut through these two. And so these cuts can also be derived for more general constraints. In particular, what we like to do is do relaxations of one row of the constraint sets at a time. And the continuous variables are aggregated depending on the sign of the coefficients in A here. So we then aggregate them into a positive and negative part, and then there is an inequality that we can obtain that's again a valid inequality, and that's a stronger inequality than the original constraint. So that's one way of strengthening linear inequalities. There's another approach, and that's also a classical approach by Gomery, And Gomery cuts are again given in a similar way by computing the fractional part of the constant and the variable coefficients terms, and then deriving cuts. And these cuts have been used, so people have tried to use them for mixed integer linear optimization. Sorry, they're very classical in mixed integer linear optimization, and they've been used in mixed integer nonlinear optimization to try to strengthen the outer approximation relaxations. But the improvement hasn't really been all that great. So these cuts, even though they're useful in some cases, they're probably not as strong as the ones that are based on perspective or exploiting the nonlinear cuts, such as the separability cuts that we had earlier in the morning. So for the rest, I was going to tell you a little bit about a slightly different problem that we've encountered, where we used insights into integer optimization to actually simplify a nonlinear problem. And so I have to do a little bit of a detour. This is a bit of a sort of imposition on you. So there's this is a binary quantum optimal control problem. So we're interested in a quantum system that has q qubits and n controls. And the controls you can think of as being lasers that target the qubits. There is an intrinsic Hamiltonian matrix. So in quantum systems, these Hamiltonian matrices are symmetric matrices that are of size 2 to the q by 2 to the q. So q is the number of qubits here. These are very big complex matrices. And we have these controls that we can apply at every time step. So this is a problem on a continuous time horizon. And then in addition, once we compute this control Hamiltonian, we propagate this control Hamiltonian through this equation, which is Schrödinger's equation, which is an ordinary differential equation in matrices. So the big X here are matrices, and they're unitary quantum states. So that's the state of your quantum computer. So the goal is to somehow control the Hamiltonians, or which you can think of as the gates in the quantum computer, to achieve a certain state that you want at the end. And the objective here is the final state, and typically you're trying to get to a given final state. Okay, what has this all got to do with integer variables? They're down here. So at the bottom we have that the controls are these binary controls. They're either 0 or 1, and they sum up to 1. So they're special ordered set of type 1. Okay, so all you need to worry about at this point is that we're minimizing a nonlinear function subject to maybe some nonlinear constraints, but we're doing this over the binary variables or binary controls that we have down here. So one way of thinking about this problem is, if you give me a set of binary controls, if you prescribe the binary controls, then everything in here is fully defined. So you just, once you have the binary controls, you construct your Hamiltonian, you solve this system of ordinary differential equations, and you just evaluate the objective function. So this is just a problem over integers that has a very funny looking, nasty, nonlinear objective function. And we're going to simplify this objective function. That's the goal. So before we simplify it, we can, the way we usually solve this problem is to take the time, so we have time goes from 0 to final time, and we discretize time into a finite number of, for example, equidistant time steps. And here we took equidistant steps that are of size delta t. And if we do that, then we can rewrite the controls as these piecewise controls. So now our control functions are going to be functions that are either 0 or 1 on these intervals. So I might have a control here, that's one control, and then I can have a different control that I'm so that would be one control that I could implement, for example. But I don't just have the one control, I also have to choose which of my controls I implement in each time step. And that's sort of the special ordered set of type 1 constraint. So there's one quick trick, which is if you know ordinary differential equations, then you know this trick. You can actually explicitly solve the ordinary differential equation on the time horizon from tk minus 1 to tk. So that's an ordinary differential equation that's written here by simply doing this exponentiation. So you take, this is a linear ordinary differential equation or system of linear ordinary differential equations, and the solution to it is simply taking the exponential of the right-hand side. Okay, and you can check very quickly, you can actually check this if you had, if this were just h, were just a single variable, then you can quickly check that when you differentiate this function here, you get in fact the minus IH xt out. So that's a quick double check that that's correct. Okay, so this is cool, but there's one problem in these instances, and that's that you need to form these exponentials, these matrix exponentials, and that's the hard part, and that's where the integer optimization is going to help us. So why are matrix exponentials hard? Because unfortunately, the exponential of a matrix is not just the exponential of the components. So the exponential of a matrix A that is not the same as saying I take the matrix where I just take the EIJs. So that's not correct. So forming matrix exponential is more involved, and I'm going to delete this immediately so that you don't remember it. What you need to do to form a matrix exponential is you need to get the matrix into a diagonal form. Once the matrix is in a diagonal form, then you can just exponentiate the things on the diagonal. And so to get the matrix into a diagonal form, you form an eigenvalue decomposition. And so an eigenvalue decomposition of a complex matrix is given by these orthonormal matrices Q and the diagonal matrix of eigenvalues lambda. So what you can write, you can form these this eigenvalue decomposition where this dagger is simply the complex conjugate transposed, or the Hermitian conjugate of the original matrix. Okay, and then to evaluate the matrix exponential is easy now. You simply evaluate, you take the sort of orthonormal vectors outside the exponential, you exponentiate the eigenvalues, the diagonal, and then you put it all back together afterwards. And so this is easy. So in particular, the exponentiation of a diagonal matrix is just the diagonal matrix of the exponents that you get here. So why is this difficult? Because one, these matrices are large and dense, and two, there's a fundamental problem that you need really, for each time step that we have up here, you need its own eigenvalue decomposition. Because if I go back to the solution of my ordinary differential equation here, I can just concatenate these formulas. If I took this formula, if I plugged xk minus 1 in here, then I have another matrix exponential times xk minus 2, and so on. So I have this telescoping product, and really what I want to do is I want to just form this product of matrix exponentials, but that's not the same as the exponential of the sum of these. So I can't just do this once. I need to do t of these matrix exponentials, which is very expensive. And I need to do this a lot of times, each time I want to evaluate my objective function. Okay, so the bottleneck is that if I have something like 50 optimization steps, then I might need to form something like 5,000 matrix exponentials, each matrix of the size 2 to the q or so. And this is where the punchline is. This is where the one-hot encoding helps us. We can do this trick of taking this nonlinear function that I have here, where I wrote down the matrix exponential that I want to form over every time step, and I'm actually allowed to take out the I can take the summation out of my matrix exponential because what I'm effectively doing is each time I want to do this, I select exactly one of these matrices. So what I'm evaluating here is the one-hot encoding of all the possible matrices that could be in here, but that's the same as evaluating all of these possible matrices and then doing the one-hot encoding on the result that I get. And so the advantage is, if I do this guy here, then I need to form a lot of different matrix exponentials, potentially especially if I have fractional values here. But if I do this here, I can get away with pre-computing these matrix exponentials once for any values of wjk. And so that helps me when I want to solve the relaxation. So when I solve the relaxation of this problem, I'm going to minimize over the continuous relaxation of the wjk. And if I did it in this form here, then I would have to form a lot of matrix exponentials at every iteration, because as wjk, as the fractional values change, these matrix exponentials will change, and I would have to do my factorization over and over again. Here, I do the factorization once, and I just optimize over the resulting term. And this is exact on the integers, but it's not true over the continuous. So this is only exact if you're doing this over the integers. And so this is a little example where when we're using integer variables, we can sometimes simplify nonlinear functions. And that's used in optimal control, where you can actually now rewrite some of these terms by pre-computing solutions, or by reusing the fact that you have this one-hot encoding, and it's known as outer convexification. And it means that we can solve a lot of optimal control problems that would otherwise be very hard to solve much, much easier now. Okay, so that was a little trick. I really like this trick because it sort of goes from the integer side back to the continuous side and shows you that using this integrality, you can actually sometimes simplify the nonlinear world and write a different problem. So what I've written here, this equality does not hold if you relax integrality, but because we're ultimately only interested in integer solutions, we're happy to have a different formulation. Okay, so I talked a little bit about cuts, MIR cuts and Gomery cuts, and then I showed you this formulation of a quantum optimal control problem. And I hope I didn't throw you, well, hit you over the head too much there. This outer convexification formulation is something that generalizes to many other cases. And it's a very useful modeling trick when you're dealing with optimal control problems, because it disentangles these binary controls from the differential equation. And that turns out to be an important trick for solving these problems efficiently. That was it. So with that, again, let me ask you if you have any questions.
Since you have already taken out all the binaries out from the exponential,
Yeah.
essentially becomes a redundant question. Nonetheless, can we write in general, can we write this expression of exponential over some matrix as 1 plus, can we like outer approximate it at 0, 1 plus x e power x is less than equal to 1 plus x by the
We could probably do something. I hadn't thought about that, but so you want to, it won't be 1 plus because this is a matrix.
Identity plus
Yeah. There is some identity matrix plus something. That might be an interesting idea. And then,
But since we have already taken that out anyway, now
yeah.
decomposing this becomes a redundant.
Right. So there is an approximation of the exponential that says it's 1 plus something, and that corresponds actually. If you go back, I'm going to go back, and that's a really smart comment. So that actually corresponds to using, I think, explicit Euler's method for solving this differential equation. So that reformulation is using an explicit Euler scheme on this equation. But then you don't then, when I do the matrix exponentiation, I'm actually solving the differential equation exactly over each time step. So that's why that's probably better to do. But we can do, yeah, there's lots of games one can play once we simplify the problem in this way.
With respect to that, is exponentiation a convex, is exponent of the matrix a convex function?
I honestly don't know. For real numbers it is, yes. I have no insight as to what happens in matrices. No, it's not. Oh. Yeah. Right, yeah. So because you're in complex systems, there's no ordering. So writing an inequality would be harder. That's a very good point.
What if it's a real matrix? Yeah.
I don't know. I worry because to do the matrix exponential is defined in terms of an eigenvalue decomposition, which, again, I don't know. I mean, somebody who knows more about cones can probably tell you the answer as to whether a matrix exponential is convex or not, but I don't know the answer to that. I'm sorry. Okay, somebody else would like to ask me a question that I don't know the answer to.
So this was implemented somewhere, and people work with this imaginary or complex numbers.
Yeah. And there are algorithms for solving the continuous relaxation, and so they are usually gradient descent methods. But you can only solve very small systems, so you can't go more than a small number of qubits, maybe 8 or so, because the matrices become very large, and they also tend to be dense matrices. So that's why it's expensive. Okay.
So this exponential will also generate a complex matrix.
Correct. Yeah. If you look back here, yeah. So these matrices are complex valued matrices, and so you then have a diagonal, which is the matrix exponential here is just it generates a complex matrix again. Yeah.
The eigenvalue decomposition is the same.
That's the same principle as for the reals. Yeah. Okay.
All right.
Good.